All right, so recording is rolling. It is Tuesday, November 29. I have a lab lineup for you guys. I just gave you guys this page. Right, so the review torque a little bit with you guys, throw you guys a challenge question, and then demo this lab for you guys. Okay, so one time here. So yesterday was a notes day. I took you guys through a bunch of notes about rotational dynamics concepts. We went through all these slides and then these here. Right, so you guys got a bunch of concepts, but one of the important concepts was this idea of torque. Right, so torque, sometimes called moment, like a turning moment. This is R cross F, so radial distance across the force. Opening a door is a classic example. So is a wrench turning a nut, just like this picture. Right, so if you apply a force at some radial distance, you can get this turning moment, but only the perpendicular components of those two multiplied together actually count towards torque. That's what a cross product is, sometimes called R times F times sine theta. If you have the angle between those two vectors, right? So get careful about that angle, because if you're ever throwing this angle here, that'll be not sine but cosine now, right? If you had this angle, right? But usually you're given this angle, which is this angle, right? Torque is also equal to I times alpha. You can set these equal to each other and solve for problems. That's not exactly the way we're going with this today, but there could be other type problems. Okay. So we got torque. Okay. All right, so here's your challenge question. You guys see this this spool? It's two different radial sizes. I got this outside radial size and then this inside radius. You guys see that? Okay, two different radial sizes. I got the string wound around this thing. So let me draw that picture for you guys. Okay, it's gonna look like outside radius, inside radius, and this I'm going to park it vertical on the ground. Here's going to be the ground. Okay, this thing has a string round around on the inside wheel, right? Okay. And first thing we're going to do, okay. Actually, I got a couple of questions for you guys. This first one I think is going to be pretty straightforward. I hope. We'll see. If I pull straight up on the string, okay, then okay, draw that here. Okay. So I'm going to apply an upward force on the string. I call this F1, okay, first force. Is this whole wheel going to rotate counterclockwise to the left, or is it going to rotate clockwise to the right? Okay. Let me see, show hands. How many guys think it's going to rotate counterclockwise to the left? Who says counterclockwise to the left? Oh, look at all those hands. Look at all those hands. Does anybody say clockwise to the right? Anybody say that? No, nobody says that? Yeah, let's check this out. Yeah, it is counterclockwise to the left. Look at that. You guys are right. Okay. Ooh, do you think there's some kind of torque involved? Right? Some kind of force times lever arm? Right? You guys see what the lever arm might be? So we'll draw this yet, but let's sort of come back to that. How about this though? Right now, here's the actual challenge question. What if I don't pull straight up? What if I pull horizontal? So if I pull a string horizontal, okay. Now which way is this going to rotate? So let's see here. Call this F2. Okay, so same options as before. So is this still gonna rotate counterclockwise to the left, or is it gonna rotate clockwise to the right? There's a few seconds to think about that. So I asked my AP kids this morning, and it was about a 50-50 split. So see how you guys do. All right, so when I pull horizontal to the right, F2. Let's see, show hands. How many guys think this is still going to go counterclockwise to the left, just like before? Okay, so I've got some votes on that. Who says it's going to go clockwise to the right? Ooh, got some votes there too. This is about 50-50 split also. Okay. So let's do some science. Find out what's the actual answer. Oh, it is clockwise to the right. Look at that. There's more string here. Clockwise to the right. Look at that. Okay. So there's also torque involved. So something to do with R cross F. Now, if you said counterclockwise to the left, I have to guess why you would have thought that. You may have been looking at the center of the circle and said, well, if this was the lever arm and this was the force that looks like counterclockwise, but that's actually not. This is actually not the lever arm. The lever arm is actually right here, because this is like the pivot point that's actually rotating about. It's not actually rotating about the center of the circle. it's actually rotating about this point down here. And this point's important because there's static friction with the ground, right? See, if you didn't have static friction, you wouldn't get like that type of rotation. Right? So go back to the original one where I was pulling straight up. Right? Now this was your force, and your lever arm was like right here. This was the original lever arm. I'll call this R1. Right. So this is like the width of the door, and this was like the door hinge. This was like the door handle. Right. So then that made it go counterclockwise for F1. Okay. But then for F2, now your door, like the lever arm of the door is like this. There's R2. Right. You guys see the like this turning moment, like this torque going clockwise? You guys see that? Right. So that's why that went clockwise. Hey, if I pull straight up and it goes counterclockwise, and I pull straight to the right and it goes clockwise, do you think there's somewhere I can pull in the middle where there's going to be no torque at all and no rotation? Do you think it might be like here? If this is my pivot point down here, I think it would be right there. I call that F3. You think I can pull and there could be no torque, no rotation? Let's try this out. Let's see if this actually works. Oh, look at that. It's sliding without rotating. It's sliding without rotating. I get it at just the right point. Look at there. You guys see that? Whoa, crazy, right? Okay. But that's sort of analogous to if you had, say, this wrench and you were like pushing or pulling parallel to the wrench, or same idea with the door. You push or pull parallel to the door. Right? Never turn the wrench, never turn the door because there's no torque, there's no turning moment. Right? Okay, guys good? All right, so you guys ready for this lab? Okay, let me get a few more lab papers out here. Who needs the lab page? Who doesn't have the lab page? Who doesn't have the lab page? Everybody's got the lab page? Too, if you change your mind, I've got some extra copies right here. All right, so this lab, we're going to do one side today, and we're going to do the other side tomorrow. Right now, at a glance, they look kind of similar, but there's a difference. So the side we're doing today, do you guys see like one spring scale pulling up and two lab weights pulling down? You guys see that? Right. So that's what we're going to focus on today. Right. Now, let me show you guys the other side just so you know what you're looking at. Right. Tomorrow, we're going to do one where there's two spring scales pulling up and one lab weight hanging down. Okay. Okay, but we'll say that for another day. Okay. So this one right here. Okay. Now, there's two halves of this, but they're really two different perspectives to the exact same phenomenon. So I'm going to demo this for you guys and send you guys back to the lab area in about 10 minutes. And what I do, all you need to do is just one setup. So just pick a couple lab weights, just put them somewhere where this can, and then put a spring scale in the middle. So this whole thing is just in equilibrium. Equilibrium, you guys know that the forces are going to balance. So the spring scale is holding up the weight of the meter stick plus the two lab weights. Okay. But also, you guys have a new condition starting from yesterday, which is that the torque also has to zero out. Okay. And the sort of goal of this lab is, see where it says mystery lab weight? Okay. You're going to make believe that you don't know what one of these lab weights is. Actually, it's sort of the inspiration for this. I know it's just too much information, but this one of these labs that I keep redesigning every year. I think I finally nailed it, like after so many years of like redesigning this thing. But the original inspiration for this comes from, in fact, the old school I used to teach at, there was like this mystery lab weight that didn't have a number on it. Like all these lab weights have number stamped on them. Like this one says 100 grams, right? So it must be 100 grams. But there was a mystery one that we pulled from the closet and it didn't have any number on it. We couldn't figure out what it was. So I said, oh, well, I know how I can figure out what this is. Right? Just take a ruler, just draw it for you guys. Right? Put it on a pivot point. Right? Now, if the ruler is sitting on the pivot point ruler, right? If it's just there at ref, actually, I'd like a meter stick, but you guys get the idea. Right? If its own center mass is on the pivot point, then there's zero torque. Everything's just balanced already, right? Then if you take a known mass and put it on one side, and you take your mystery weight and put it on the other side, right, and slide it around until it balances out, you can use torque to figure out what the mystery weight is. So like if I know, say I know 100 grams is right here, right, and then I have my mystery weight and I put it right here, okay? Then relative to this pivot point, if I'm treating this, I'm going to label this pivot. If that's my pivot point right here, then do you guys see that this weight times this radial distance, right? This R across this F is causing a counterclockwise torque. Do you guys see it? Counterclockwise, right? And then this larger weight times this smaller radial arm, right? The small R across this large F should be causing the same torque, but clockwise. So it'd be like a negative torque. So I got a positive torque versus a negative torque. We sort of showed you guys right hand rule, but right, you guys got that? Right. See, one of my thumbs pointing out of the page, one of my thumbs pointing into the page. It says like positive torque versus a negative torque. Right. But we can just call it counterclockwise and clockwise. Right? You guys got that? Right. And then if you know three of those here, so torque on the left side plus the torque on the right side is 0. So the magnitudes are the same. The torque on the left, torque on the right. I got R cross F is equal to R cross F. Okay. Now, since the R and the F are at 90 degrees to each other, the radius is horizontal and the forces are vertical. Sine of 90 degrees is just 1, so I don't have to worry about sine of any components. So they're already perpendicular. Okay. If you know check, check, and check, you can solve for the mystery lab weight. Get that? Okay. So that's pretty much what I'm having you guys do here. Right? Now, you're going to know what these lab weights are, but let's make believe that you don't know this one. Okay? You guys get that? Okay. Right. So let's take a look there. Okay. I'm going to, here, I have a demo rigged up for you guys. Right. So let me flash this in front of the camera just for the video. All right, we got, let's see where you guys can see this too. Right. I got a meter stick with, see a weight there. There's in the middle, I'm going to hold this with the spring scale right here. So spring scale is going right at this point. Okay. And then I got a lab weight on this side. Yes, that. Okay. So let me take this. I've got some red spring scales back there. I think those will be pretty handy today. Got this red spring scale, just click it right in the middle. Okay. Okay. Let's bring this out here. And okay, right now it's not balanced, right? It's like it's all wonky. Okay. All right. I'm going to slide this around until it is balanced. And that is, ooh, like right there. You guys see it's, now it's a really precarious balance. You have to get it like right at the right spots, but right there, it's, stop sliding around. Try one time. You can also screw this in place so that it doesn't slide around too much. Ah, look at that, look at that. So pretty close to balance. I think it's pretty balanced right there, right? Okay. Okay. So you just need a configuration that's balanced. Now I'm going to take this exact setup. I'm going to pop some numbers into that table just so you can see what's going on. But when you guys go back to the lab area and you guys do it yourself, you can set up your own lab weights and your own distances, right? You're not going to copy exactly what I did. Okay. Okay. Like not number for number, but it could be a very similar setup. Okay. So what do we got on this table? I'll walk you guys through this process and I think it'll make sense. Okay. Oh, I should tell you guys too. So big picture point of view, both of these are the exact same setup. They're just two different perspectives. But I want you guys to see that regardless of, well, here. Let's focus on one of these first, and then you guys will see point by point. Let's start with the right side one, because the one on the right side, see where it says pivot point scale, right? Pivot point scale. I think that's like the most intuitive point to pick as your pivot point, which, by the way, is exactly what I just did for this example, right? I was treating this like the middle point as the pivot. Okay. So if you just replace its fulcrum with this spring scale pulling up, this is like the same idea as I just did, right? Okay. Right. So I think this is the most intuitive point, is the pivot point. Okay. So what is the weight on the left side? Now my weight, here, I have a 500 gram lab mass. That's what I was just showing you guys. This is like my 500 gram lab mass. Okay, it's 500 grams. How many newtons does that weigh? Yeah, about 5 newtons, right? Here, show you guys. So if you go 500 grams, divide by 1,000 to convert to kilograms, and then multiply by about 10 meters per second squared, yeah, that's like 5 newtons. Okay, so I'm going to call that a 5 Newton weight. Okay, okay. I'll leave this page up while you guys are doing your lab, but don't copy this because you guys are just going to make up your own numbers, right? You got to test your own weights. Okay, and what's this radial distance from here to here? Right? Because if this is my pivot point, then isn't this lab weight trying to cause a counterclockwise torque relative to that pivot point? So I need this radial distance. Isn't that true? Radial distance, right? Which is the difference between these two. Okay? So mine was at the 30 centimeter mark. If you do 30 centimeters minus 50 centimeters, guess what's 30 minus 50? big -20. Notice I gave you guys a negative sign here because this number will always be, I mean, if it's to the left of the scale, it's got to be negative, right? Okay, so helping you guys out, it has to be negative. Torque, is torque equal to R cross F? What is 5 times -20? -100. Okay? And the unit would be Newton centimeters. Okay? Oh, so torque is measured in Newton meters or Newton centimeters, some kind of force times distance. Right? No, side thought here. You might be tempted to call that some version of joules. Is it Newtons times meters joules? Right? But that's not true for torque. So for torque, never call it joules, even though it might look like it. We'd call it Newton meters, in this case, Newton centimeters. All right. How about the weight the weight of the meter stick? Right. Now, the weight of the meter stick, true, it is distributed over the entire length of the meter stick, but it's perfectly fine for this type of application to treat the entire mass and the entire weight of the meter stick as though it's acting at its own center of mass, right, which is at the 50 centimeter mark. We should be pretty close to the 50 centimeter mark, just to make a little bit of an assumption here. Okay. But if that point, by the way, it should weigh about 0.1 newtons. I was getting about maybe about 0.12 newtons, going to be a bit more precise. Right? There's some scales back there. There's an electronics balance, and there's also a triple beam balance. So you guys can measure this more exactly if you want, right? But in this case, it doesn't matter anyway, because the fact that it is at the point that we've defined as the pivot point, it's kind of like pushing on the hinges of the door. That's never going to open the door. Or in this case, like in the case of the wrench, if I go up and I start pushing on the wrench right here, that's never going to turn this nut, right? Okay. So any force that's at the defined pivot point zeroes out in terms of torque. Sometimes it's really helpful if you're solving problems, you can define the pivot point at blah, 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 to cancel out one of the forces. Okay, so it's going to zero out anyway, right? Okay. How about the weight on the right? Now, my other weight was 200 grams. 200 grams was a lot of mass. So guys, 200 grams. How much does that weigh? Or I'm so sorry, I'm getting ahead of myself. I didn't actually read my own paper, right? The force rating from the scale. The force rating from the scale, well, here, I'm going to tell you guys it was 7.1 newtons. Okay, so if I was holding it up doing the demo, it would be like 7.1 newtons. So let's run with that. But again, if that's at the point of what's defined as the pivot point, then whatever force times 0 centimeters away from itself, still 0 torque relative to that point. That makes sense. Okay. So far we've accounted for like 3 torques, and 2 of those are just equal to 0. Okay. So there's really only 1 torque relative to this point that we've accounted for, and that's this lab weight trying to cause a counterclockwise torque. Okay, that. So it must be the case that this guy has an equal and opposite torque. Wouldn't that be true to balance out this torque? Right? Right. So the sum of the torques is -100 plus 0 plus 0. Isn't that just -100 Newton centimeters? Right. So for this particular setup, whatever this number is, just copy paste it right there. Right. Right. Now, if the torque from the left side is -100 Newton centimeters, then what is the torque from the right side? Positive 100. So does that number go right here? Torque on the right side, positive 100 Newton centimeters. Right. One of the two. Okay. And the distance away was well, it was at the far end of the meter stick, which is 50 centimeters away. So this is 50. Is that okay? 100 minus 50 is 50. Right. So that number goes right here. 100 minus 50 is 50 centimeters. Right. The unit centimeters. Okay. And if torque is equal to R cross F, then guys, 50 times what is equal to 100? 2. And the unit is newtons. So it should be a 2 Newton weight. Is that true? Oh, let me clip it off here and flash this in front of the video. It's this guy right here. It's 200 grams. Hey, 200 grams. Does that weigh 2 newtons? Yeah, sure does. So we got it right. Right. Again, the assumption that we started with was that we didn't know what this was. It was like a mystery weight. So it was like wrapped in paper, some mystery box. Okay. But we figured it out anyway, and we could very quickly confirm that because we know that's what the answer would be. Right. Is that okay? Thanks for that. Right, so you guys can do your own setup, and then should come out really close to what the actual answer is. Okay. All right. How about the left side of this paper? Now, the left side of this paper is the exact same setup, so you don't actually have to change anything physically. You can use same meter stick, same weight, same location, same spring scale, but none of those things change. Okay. What does change is your perspective. Notice in bold here, what we just did said pivot point was defined at the point of the scale. But this one says the pivot point is defined as the 0 centimeter mark. Huh. Right. So Now, this is a really abstract idea, but mathematically, it's actually going to be more straightforward. But the idea is more abstract, and that's that I'm treating this point right here as the pivot point. We're defining this as the pivot, okay? Which at a glance wouldn't make any sense because there's nothing going on there. It's just a 0 centimeter mark, right? There's no forces there, right? So the big idea that I'm trying to get at with this is that you don't actually have to pick any particular location as the pivot point. You can technically pick any point in the whole universe as the pivot point and sum the torque about it, and the torque should still sum to 0, and therefore you can still solve for this mystery weight. Okay, you guys good with that? All right, so let's see if that actually works, because it's kind of an odd idea. Okay. So the weight on the left is the same as it was before. I had a 5 Newton weight before, it's still 5 Newtons. Now its location. Before I did 30 minus 50 to get negative 20. But if it is at 30, 30 minus 0 is just 30, isn't it? So wouldn't this just be 30? So relative to this endpoint, wouldn't this be sort of trying to cause a clockwise torque of 5 times 30 is 150 Newton centimeters? Okay. Right. Right. And then the weight of the meter stick itself is should be tiny. It should be a little bit bigger than that, but pretty close to that. Right. So about 5 Newton centimeters of clockwise torque, very small clockwise torque, again, relative to this defined pivot point. Okay. But the scale, the scale should be pulling back with a huge counterclockwise torque, right? Because it's got to balance everything out. And then finally, this mystery weight appears causing a clockwise torque, right? So relative to this point, you guys see 4 torques, clockwise, little clockwise, big counterclockwise, and a clockwise. You guys see that? Okay. Right, so the scale reading, remember, was 7.1 Newtons from before. That's not going to change. That's still 7.1 Newtons. And I gave you guys the negative sign because we'll call up negative and down positive. Okay. Okay. All right. So what is negative 7.1 Newtons times 50 centimeters? That's negative 355 Newton centimeters. Okay. Okay. That okay? All right. So if you add up those 3 torques, clockwise, little clockwise, big counterclockwise, out of those 3 torques, let's see what they add up to be. 150 plus 5 plus negative 355. I'm looking at negative 200 Newton centimeters. Okay. Okay. That okay? Right. And then if these 3 guys, the sum of those torques is negative 200 Newton centimeters, then what is the final torque equal to? It must be positive 200 Newton centimeters, because that would zero out the total torque, right? These 3 guys together is negative 200, so this guy must be positive 200, right? So whatever this box is, just take the negative of that, just make it positive, okay? All right, right. And then that location happened to be the full end of the meter stick. So wouldn't this distance be 100 centimeters, right? 100 minus 0 is 0, or sorry, 100 minus 0 is 100. So it is that 100 centimeter mark. Get that location. Okay. And then finally, here's the last step. Guys, 100 times what is equal to 200? 2. And the unit is Newtons. Oh, hey, that's the same way before. Look at that. Okay. So the first way I did it was like the more intuitive way. Treat this as the pivot point. It came out to 2 Newtons was the mystery weight. Okay. The way we just did it is this more abstract way to do it. We just picked a random point, like the 0 centimeter point is the pivot point. Okay. Still sum the torque about it, zeroed it out. And the mystery weight still came out to 2 Newtons, of course. Right? Now, do you guys think you can go back to the lab area, come up with your own lab weights and slide them around and do something very similar to this, just different numbers? Right? All right. So you guys got the rest of the day to do this. I'll walk around and help you guys out, and we'll save the backside of this for tomorrow.